Good morning everyone. Today my group and I will present our project about continuity and discontinuity in mathematics. This idea also appear in real life. For example, in tax system. Our group members are Hakim, Ryan, Andy Ryan, Paul Gilbert, Muhammad Nur Aziz dan Ahmad Arshad. Okay, let's start with the basic.
Hi, my name is Paul Gilbert. My metric number is DB240068. Now I want to present introduction about concept of continuity and discontinuity in function. Alright, a function is continuous if its graph is moved with no breaks, jump or gaps. This means that small change in the input produce small and predictable change in the output. On the other hand, a discontinuity occurs when this smooth behavior fails. This can happen at hole in the graph, sudden jump, vertical asymptotes, or when the function oscillates wildly. In short, continuity ensures stability and predictability in a function, when discontinuity shows a point where the function behaves unexpectedly. Okay, now we go to continuity and discontinuity. Okay, a function is continuous at the point if its graph is moved without any break, jump, or holes. There are three conditions for a function to be continuous at x equal to a. Number one, the function exists at the point, meaning f a is defined. The limit exists as x approach a, meaning limit fx exists. Number 3, the limit equal the function value, meaning limit fx equal fa. For example, fa equal x2 is continuous for a real number because at every point the function has a value, the limit exists, and the graph is smooth. Similarly, fx equal 3x plus 2 is continuous everywhere because it is a straight line. On the other hand, a discontinuity occurs when any of these conditions fail, causing the graph to have a break, jump, or vertical asymptote. Okay, now we go to the types of discontinuities. First, removable discontinuity. This happens when there is a hole in the graph. The function has a limit at the point, but it is either not defined there or its value does not match the limit. For example, consider a function where we divide x squared minus 1 by x minus 1. At 1, the function is not defined, but the limit exists and is equal to the 2. If we define the function to be 2 at the point, the hole can be removed. Second is a jump discontinuity. This occurs when the graph suddenly jumps from one value to other. The left hand and right hand limits exist, but they are not equal. For example, imagine a function that equals 1 for a value less than 0 and equal 2 for 0 and above. At 0, the graph jumps from 1 to 2. The third is a oscillatory discontinuity. This happens when the function keeps swinging up and down as it approaches a point, so the limit does not exist. For example, a function that is the sine of 1 divided by x keeps oscillating between minus 1 and 1 as x approaches 0. Next, we go to the important theorem related to continuity. First, the intermediate value theorem. This theorem says that if a function is continuous on a closed interval, then it takes every value between the function value at the ends of the interval. In other words, if the function starts at one value and at another, it must pass through all the value in between. For example, if we have a function like x cubed minus x minus 2, there is at least one root between 1 and 2 because the function changed from negative to positive. Second, continuity of composite function. If one function is continuous at a point and another function is continuous at the value of the first function, then their combination or composite function is also continuous at the point. This is useful when we have function defined in terms of other function, for example sin of x squared. Third, the extreme value theorem. This theorem says that if a function is continuous on a closed interval, it must have both a maximum and a minimum value somewhere in that interval. This is very useful in optimized problem because it guarantees that continuous functions reach their highest and lowest point on the bounded interval. So this three theorems, immediately value theorem, continuity of composite function, and extreme value theorem, a very important tool in calculus. Now let's talk about the connection between limit and continuity. The idea of limit is very important for understanding continuity. A limit tells us the value of function is approaching as the input gets closer to a certain point, even if the function is not actually defined at that point. Continuity, on the other hand, requires that the function actual value at the point match the value is it approaching, which is limit. In other words, a function is continuous at a point if the limit of the function is approach that point exists and equal to the function value there. So limit show the intent value for the function, and continuity ensure that the function actually reach that value. A function is continuous if this is true at every point in its domain. So that for my present.
Hi, my name is Muhammad Hakim bin Jaafar. My matrix number is DB240004. I will continue first for this section, which is function analysis. Then my friend will continue the later part. So let's start with a piecewise function that have jump discontinuity. Okay, let's look at this function. Okay, f of x equal 2x plus 1 when x is less than 2, 5 when x equal to, and x squared minus 1 when x is greater than 2. Now let's analyze it at x and equal to. First thing we need to do is we need to find the limits. So let's start with the left hand limits. We look at the part 2x plus 1 as x approach 2 from the left. Then we substitute 2 into 2 times 2 plus 1 equal 5. So the left hand limit is 5. Then we go to the right hand limit. We look at the part x squared minus 1 as x approach 2 from the right. Substitute 2 into 2 square minus 1 equal 3. So the right hand limit is 3. So the f of 2 equal 5. Then we compare the limits. We compare the limit. We get left hand limit is 5. Right hand limit is 3. They are not equal. The limit does not exist. The function jump at x equal 2. This is called a jump discontinuity. As we can see in the graph given, from the left side, straight line approaching coordinate x 2 and coordinate y is 5. And then we look at the right side, the parabola starting at 2, of which the coordinate of x is 2 and coordinate of y is 3. The graph jumped from the 5 to 3 at x equal 2. Hence, this is only my part.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Razidin Zainal. So, the rational function, oscillatory discontinuity. So, our final example cover the most complex type of discontinuity. The function we are analyzing today is fx. It is defined for all x values except x equal 0. Fx is equal to the sine of the quantity 1 divided by x. So we immediately look at the point where the function is undefined, which is x equals 0, as the term 1 per x will involve division by 0. Therefore, the function value x at x equals 0 is undefined, which is our first condition for discontinuity. The current part of the analysis comes when we look at the limits, both from the left and the right, as x gets extremely close to 0. The argument of the sine function 1 per x approach either positive or negative infinity. Because of this, the function value oscillates infinitely between -1 and 1 as x approach 0. It never settles on a single number. Therefore, the left hand limit and the right hand limit do not exist. So, our final conclusion is clear. The function is discontinuous at x equals 0. So this is an oscillatory discontinuity because the limit does not exist due to infinite oscillation. Let's look at the graph that visualize this behavior. As the graph descriptions notes, for x not equal to 0, the graph oscillates faster and faster as it gets closer to the origin. Near x equals 0, the function is swing between -1 and 1 infinitely many times. Because the limit does not approach a single infinite discontinuity critical asymptote. Gx is equal to 1 divided by the quantity x minus 2. We immediately see that the function is undefined when the denominator is 0, which happens when x equal 2. This is due to division by 0. To classify discontinuity, we must examine the one side limit as x approach 2. So the limit of gx as x approach 2 from the negative side is a negative infinity. This means that as x gets very close to 2 but remains slightly less than 2, like 1.99, the denominator is a very small -1. 1 divided by a tiny negative number results in a negative number, so the function dives down. Okay, right hand limit. So the limit of a gx as x approach 2 from the positive side is a positive infinity. As x gets very close to 2 but remains slightly greater than 2, like 2.01, the denominator is a very small positive number. 1 divided by a tiny positive number results in a half positive number, so the function shoots up. So the conclusion is, since the function approach positive infinity, 1 on the side and negative infinity on the other, the two side limit does not exist, and we conclude the function is discontinuous at x equal to. So let's look at the graph. The graph clearly approach a vertical line at x equal to. So this is at the vertical asymptote. As x approach 2 from the left, the graph goes down to negative infinity, and approach 2 from the right, the graph goes up to positive infinity. The infinite discontinuity divided the function into two separate branches that can never connect, which is why this is another example for an accidentally discontinuity.
Assalamualaikum, my name is Ahmad Arshad bin Abdul Samad. Today I would like to share with you real life situation about continuous tax rate. It's about progressive tax system with smooth bracket. Some country design tax system that your tax change gradually as income increase. So this make the tax paid a continuous function, no sudden jump. For this slide, allow me to explain an example of a tax function that is expressed as a piecewise function. This function t bracket x apply two different tax rates based on a person income level. An individual earn up to 20,000 ringgit, the tax rate is 5%. However, once the income exceeds 20,000, the first 20,000 remain taxed at 5%, while only the amount above that threshold is taxed at 10%. This setup reflects a realistic tax system where higher income levels are taxed at a higher rate. Now, what makes this function interesting is that it's continuous. To understand why, we examine that value at the boundary point, which is exactly 20,000. Using the first rule, 5% of 20,000 give a tax of 1,000 ringgit. Using the second rule, the calculation is result in 1,000 ringgit because the excess amount beyond 20,000 is zero. Since both rules produce exactly same value at this transition point, there's no sudden jump or break in the graph. This smooth connection is what makes the tax function continuous, and it demonstrates how a well-designed system avoids unfair or abrupt change.
Hello guys, my name is Andy Ryan Ana Aseng, metric number DB240124, So now I will explain second real life situation for part C, which is discontinuous tax rate. So this tax rate is a sudden jump at income threshold. Some tax systems have a cliff. This means if your income crosses a certain amount, your tax will be suddenly jumps, and this creates a discontinuity. Now we are going to look at a simple tax function, which is we call T of X. There are three rules based on your incomes. Rule number one, if your income or X is less than 10,000, you don't have to pay any tax. So T of X equals 0. The second rule, if your income is less than 10,000, you suddenly have to pay 1,000 in tax. So T of X equals 1,000. And the last, third rule, for income above 10,000, a 15% tax rate applies. So T of X equals 0.15x, or 15% of your income. Now the question is, why is this function discontinuous at x equals 10,000? A continuous function should have a smooth transition, but watch what happens as we approach this income level from two different directions. The first direction is the left hand limit. This is the tax you pay for income, just a tiny bit less than 10,000. So, since we are below 10,000, the first rule applies for T of X is 0. So the left hand limit is 0. Now let's look at the right hand limit. This is the tax you pay for income, just a tiny more than 10,000. Here, the third rule applies, the 15% tax rate. Now, if we calculate 15% of 10,000, we get 1,500. So the right hand limit is 1,500. And finally, let's look at the value of the point itself. This is the tax you pay when your income is exactly 10,000. The second rule tells us this value is 1,000. Now look at our three numbers: 0, 1,000, and 1,500. So the left hand limit is 0. The value at the point is 1,000, and the right hand limit is 1,500. Because of the left limit, the value at the point and the right limit are not all the same. So this function is discontinuous. Specifically, the tax payment instantly jumps from 0 to 1,000 and then instantly jumps again to 1,500 as you cross the 10,000 mark. This is what we call a jump discontinuity. This highlights why continuous functions are essential in real-world modeling to avoid sudden irrational jumps in value like this.
Hello guys, it's me again. Now, I have some question for you, which is, why is continuous tax system better for people? And how does a jump in tax relate to jump discontinuity? That's all for me. Bye.